Everyone, we are the group 11 and today we will discuss about the relationship between land contraction and time dilation and use this to derive the land contraction which is under the chapter 1 about relativity. But before anything else, let me present to you our learning objectives. So at the end of this video lesson, students will be able to understand the concept of land contraction and time dilation in special relativity, explore the relationship between land contraction and time dilation, and lastly, derive the equation for land contraction using the concepts of time dilation.
To start off, let's talk about the basic premise of special relativity. The theory was developed by Albert Einstein in the early 20th century and revolutionized our understanding of the universe. It is based on two postulates. The laws of physics are the same in all inertial reference frames, and the speed of light in a vacuum is constant for all observers, regardless of their motion. So basically, special relativity provides us with an explanation of how speed affects mass, time, and space. One of the most famous equations associated with special relativity, E equals mc squared. This equation relates energy and mass through the speed of light. It signifies that even small amounts of mass can be converted into enormous amount of energy. Conversely, it implies that energy can condense into mass under certain conditions. Let's break down the equation. E equals mc squared. The E represents energy, m denotes mass, and c symbolizes the speed of light, which is approximately 3 times 10 raised 8 meters per second. This equation demonstrates that energy and mass are interchangeable, and the conversion factor in the speed of light squared. What this equation implies is profound. It means that a tiny amount of mass can yield an enormous amount of energy. We have witnessed the practical implication of this equation in nuclear reactions, where a small amount of mass is converted into an immense release of energy, as seen in atomic bombs or nuclear power plants. Moving on, special relativity also introduced two other key concepts: time dilation and length contraction. These phenomena arise due to the fundamental postulates of special relativity. Time dilation is a concept that deals with how time can pass at different rates for different objects or in different situations. It happens when two objects are moving relative to each other or when they are in different gravitational fields. Let's imagine two people, Alice and Bob. Alice is in a spaceship traveling very fast, while Bob is on Earth. Because Alice is moving so fast, time appears to pass slower for her compared to Bob on Earth. It's like they are in different time zones, but it's not because of distance, it's because of their relative motion. So, time dilation means that time can flow at different rates depending on how fast you are moving, or the strength of the gravitational field you are in. It's a fascinating aspect of physics that shows us how our perception of time can change based on our relative motion or the presence of massive objects. The figure shows an astronaut measures the time for the light to travel distance 2D in the astronaut's frame. A NASA scientist on Earth sees the light follow a longer path to us and take a longer time. These triangles are used to find the relationship between the two of distance
So the formula for the time dilation is given by t equals t0 over the square root of 1 minus v squared over c squared, where t is the time observed, t0 is the time observed at rest, v is the velocity of the object, and c is the velocity of light in a vacuum, which is equivalent of 3 times 10 raised to 8 meter per second squared. Now let's try to answer this sample problem about time dilation. Determine the relativistic time if t0 is 7 years and the velocity of the object is 0.55. So to solve this problem, since we already know the formula, let's distribute the values given. This will result to 7 years over the square root of 1 minus v squared, which is 0.55 over c squared, which is the constant for the velocity of light, 3 times 10 raised to 8 meter per second squared. And the final answer would be 8.38 years. Length contraction. So length contraction is a phenomenon predicted by the theory of special relativity, where the length of an object appears to be shorter in the direction of motion when it moves at high speeds relative to an observer. So this means that an object moving at high speed will appear to be shorter than an identical object that is stationary relative to the observer. So basically, length contraction is a concept in physics that describes how objects can appear shorter when they are moving at a very high speeds relative to an observer. So it's all about how the length of an object seems to shrink in the direction it's moving. So imagine you have a long object like a ruler that is stationary relative to you as an observer. If you were to measure the length of this ruler, you would get a certain value. However, if that same ruler were to start moving very fast in the same direction as you, something interesting will happen. The ruler will appear shorter to you compared to its original length when it was stationary. So, it is important to note that length contraction is not a result of the object physically changing its size or shape. It is a consequence of how space and time are interconnected according to special relativity. So as an object moves faster and faster, its measurement in the direction of motion gets compressed or contracted from the perspective of an observer who is not moving at the same speed. So, in simple terms, length contraction means that objects appear shorter when they are moving at a very high speeds compared to when they are at rest relative to an observer. So, this is a fascinating aspect of special relativity that shows how our perception of the size of objects can change depending on their motion. Now, let's move forward to the formula for the length contraction. So the formula for the length contraction is L equals L0 square root of 1 minus V squared over C squared, where L is the length of an object with its relativistic speed, L0 is the length of an object at rest, C is the velocity of light, and V is the velocity of the object. Now, let's try to solve the sample problem about length contraction. An object of length 20 meters travels at a velocity of 0.65 c. Calculate the length contraction. So, since we already know the formula for the length contraction, let us now distribute the given values. So, this will give us L equals 20 times the square root of 1 minus V squared, which is 0.65 squared, over C squared, which is 3 times 10 raised to 8 meter per second squared. This will then give us the final answer of 15.198 meters. Now, since we're done discussing the two concepts, which is the time dilation and length contraction, let us now identify the relationship between these two. So, the relationship between the time dilation and length contraction is intimately connected. So, as an object's speed increases, its time dilation factor increases, causing time to slow down for that object. Simultaneously, its length contraction factor increases, making the object appear shorter in the direction of motion. So, by understanding this relationship between the two concepts, we can derive now the length contraction equation.
So good day everyone, I am Erin Umbao and I will be discussing all about the derivation of length contraction from time dilation. So how to derive length contraction formula from time dilation? Knowing that the time dilation formula is t prime is equal to t over square root of 1 minus v squared over c squared, where t prime is the time that is observed in moving reference frame and t is the time interval measured in the stationary reference frame, and v is the relative velocity between the two frames and c is the speed of light. To elaborate the derivation of length contraction, let me introduce to you a term which is very salient in explaining and elaborating the derivation of length contraction from time dilation. So, as you heard kaganina, I mentioned the term reference frame. So, unsa din ni si reference frame? It is a system of coordinates that we use to describe the position and motion of objects. So basically, it is a way of defining where things are and how they are moving by providing a fixed set of axes that we use to measure distance and time. So reference frame describe the moving and at rest object. There are two types of reference frame. We have the stationary and then the moving reference frame. So a stationary reference frame is also called an inertial reference frame. It is one that is at rest or moving with constant velocity. In this reference frame, objects appear to follow Newton's laws of motion, and there is no acceleration or fictitious forces. On the other hand, a moving reference frame, also called a non-inertial reference frame, it is one that is accelerating or rotating. To understand the difference between the two frames, consider an example of a train moving along a track. From the perspective of a person on the train appears to be at rest, and the track and the surroundings appear to be moving backward. This is a moving reference frame. And then from the perspective of a person standing outside the train appears to be moving and the surroundings appear to be stationary. So this is a stationary reference frame. The choice of reference frame can affect the measurements and observations made by an observer. For example, in the moving reference frame of the train, the length of the train appears to be shorter due to the length contraction, as measured by an observer in a stationary reference frame. Conversely, the time appears to be slower in a moving reference frame as measured by an observer in a stationary reference frame due to time dilation. Now that we understand what is reference frame, let's now proceed on how to derive length contraction formula from time dilation. So, imagine you are an observer at rest on Earth. We denote your reference frame by B. We denote the time that passes on your clock by T. At time T is equals to 0. A spacecraft flies past the observer B with a constant velocity v. It travels to a planet, let's call it Alpha, and arrives there at some specific time. So let us denote the reference frame of the spacecraft as A prime, and the time on the clock in the spacecraft as T prime. Now what does the captain see in the spaceship when he considers himself at rest? From his point of view and the point of view sa captain, the spaceship is resting while the Earth is moving away from him with the velocity v, and the planet Alpha is moving towards him with the velocity v. So the captain in the spaceship measures on his watch how long it takes him to get from Earth to katong planet nga Alpha. We denote this time span by delta t prime. And also the observer on Earth measures the time span on his clock in which the spaceship needs from Earth to planet Alpha. He denotes his measured time span with delta t. In deriving time dilation using a light clock, we found that the time spans in different reference frames are fundamentally different. Therefore, we cannot simply assume that the time span or the delta t and delta t prime are equal. we have to deduce that the two time spans of different reference frames are related by the relative velocity, or the v, as follows. So here c is the speed of light, and the prefactor in the formula is usually abbreviated as kanang murag y and called Lorentz factor. Since we know that the magnitude of the relative velocity at which the Earth is moving away from the spaceship is v, we can use the time period delta prime to calculate the distance of delta x prime that the spaceship must travel from the Earth to the planet Alpha. And from the point of view of the observer on Earth B, the spaceship needs the time span delta t, and the spaceship moves away with a velocity v. Therefore, the travel distance as x in that reference frame B is to be calculated as follows. So we have delta x equals to v multiplied by delta t. Now we can substitute the time span from equation 1 into equation 3. We have delta x is equals to v times y, or the Lorentz factor, times delta t. Our goal is to find out how the delta x prime and the distances delta x are related. Therefore, we have to express delta t prime from Captain's time to get from Earth to planet Alpha from equation 4 with delta x. To do this, rearrange equation 2 for the time period delta t prime and insert it into equation 4. So we have delta x is equals to v times y times delta x prime over v. Cancel velocity v and rearrange equation for delta x prime. We are done. If we now insert the Lorentz factor, we get the formula for the length contraction. Since the reciprocal of y is always less than 1, we can say from equation 7 the distance, or the travel distance of the spaceship from the point of view of the spaceship, or the delta x prime, is less than delta x nga nag-traveled sa distance in the reference frame na b. In other words, the delta x prime, the distance of the Earth and planet Alpha from the perspective of the spaceship, must be shorter than from the perspective of the observer on Earth. The distance Earth or planet is contracted from the point of view of the spaceship.